Hi there, welcome to the second video of the electric fields. So we'll carry on. So here we have some electric fields set up by having two conductors going through a perspex sheet, and you can see the lines created by the filings that have been placed onto the sheet. So what do the field lines mean? Well, the spacing of the field lines is important. So I'll draw some examples here. The spacing tells you about the strength of the field. So with this one here, the strength of the field going along here is constant. Well, in this one here, the strength of the field is getting weaker as you go along because the field lines are getting further apart. And on this one here, the strength of the field is getting stronger. Okay, the other thing that the field lines show is the direction. So we have this one here. A positive test charge will feel a force if it was placed in the electric field. So if I create an electric field, and in this electric field I place a positive test charge, that positive test charge will feel a force. Now if I indicate the direction of the field as being this way, then the direction the positive test charge will feel the force is in the same direction. Okay. If we had a negative test charge, or a negative charge, the force that will feel will be in the opposite direction. So drawing some field lines, if I've got two charges here, one positive, one negative, the field from them is actually what we call a radial field. So remember, from a positive charge, the field lines must be going away from the positive charge because that's the way the field will feel the force. Okay, so they're out this way here. So with the negative is going towards it. So we'll draw them in. And there we go. A couple of things to note. You can see the field lines as you go out are getting further apart. So that means the electric field strength must be decreasing as you go out. And the other thing to note is that the connection of the field line to the charge is always going to be at 90 degrees. Okay, so we have two charges that are essentially within the region that they can feel the effects of each other. So here I'll put in the charges on each one. So we've got a positive and negative up here, and a positive and positive down there. So just drawing the field lines around these. Now the positive and negative are actually going to join up the field lines because they're attractive. It's not the prettiest diagram. Remember, it goes positive to negative, so it's away from the positive. It's the way a positive test charge would move if it was placed in the field. Okay, so now if I draw the field lines for the positive, these are repulsive, so the field lines are not going to join, they're actually going to get pushed away from each other. And remember, the field line points in the direction away from the charge, the positive test charge. And in this point here in the very middle there, you'd actually get a region where there would be balanced out of electric field, so there'd actually be no electric field at that point. Last one here, these are what we call parallel plates. Okay, so these are just some metal plates, okay, just pieces of metal cut in a square and are parallel to each other. The electric field from these are uniform, and that's why they're very handy and for us, especially in calculations and so on. But the field lines are nice and parallel like this. If this was a positive plate and that was a negative plate, then they must be going down like that. Now, defining electric field strength, okay, we define it by if we put a positive charge into a electric field, then that positive charge will feel a force, and we define it by the size of that force compared to the size of the charge. So the definition is defined by the word equation. Oops, sorry about that. Okay, so defined by the word equation, electric field strength is equal to force per unit positive charge. Okay, so what's the equation? E equals F divided by Q. You could use large Q or small q. Large Q usually denotes a collection of charges, while small q would be a specific charge, like the charge on an electron. And so, looking at these examples here, we've got to calculate the size of the force on an electron if it's placed in an electric field strength of 300 newtons per coulomb. So we're looking for force here, and we've got an electric field strength E, and we're trying to find the force on it. Usually, if you look at that equation there, we also need Q. We do know Q because we know the charge on an electron. Okay, so F equals EQ, with that formula rearranged. And just a side note, Q, the charge on an electron, is 1.6 times 10 to the minus 19 coulombs. Calculate the acceleration of the electron. Well, we're into kinematics or dynamics there, so just remember the formula, F equals ma.